All right, let's get started. Good morning, good afternoon, and good evening. Welcome to Industrial Ecology Day 2021 poster session for the Asian Pacific region. And first of all, I would like to thank the poster session organizers for lining up everything nicely. My name is Zhi. I'm currently assistant professor from University of Antwerp. I'm very glad to see everyone joining from around the world. Today we are gonna hear posters covering a wide range of topics, including MFA using trade-linked method or dynamic stock flow methods, and also environmental footprinting using life cycle assessment and input-output methods. We will also see diversity in the scope of our posters covering, economy-wide material cycles, urban systems, built environment systems, waste management systems, transportation systems, etc. And before we get started, I would like to walk you through several practicalities. So first of all, to ensure smooth transitions between posters, I will share my screen and navigate the posters from my side. And of course, if you have some slides prepared, you're more than welcome to give your pitch from your side. And also, we will use a timer to control the time, so we won't have any significant delay. And after the poster session, we will have 1 hour in Wonder for networking and for further discussions about the posters. And we also ask all poster presenters to stay in the lounge they are assigned to. So we have assigned our poster presenters to 3 lounges. So you will find your lounge in Wonder. And last, we also have the possibility to cast our favorite posters. So each IAS-IE member can cast up to 3 votes, and the deadline for voting is the 23rd of June. Okay, without further ado, I would like to pass the floor to our first presenter, Ruyu Koide. Okay, let me share my screen.
Should I share the screen myself?
Oh yeah, that's okay. Yeah.
But I think it's not allowed. So
yeah, I can give you the right to share your screen. Just 1 sec.
I hope you can see my screen.
Yeah.
So just can I start or? Okay, so I think I can start, right?
Yeah, go ahead.
Yeah, okay. So hello, everyone. My name is Ryu Koide with National Institute for Environmental Studies. So our poster is about climate change mitigation through behavior changes and its comparison between multiple cities. As you know, lifestyle change has been emphasized as an important pillar for addressing climate change, especially urban consumer has enormous carbon footprint. However, existing studies on the impact from lifestyle changes are limited to country or regional level and does not consider heterogeneity within a country. So that's why our study proposes a methodology for modeling city-specific carbon footprint reduction pathways through lifestyle changes. So we conducted a case study of 52 Japanese cities for 65 lifestyle change options covering mobility, food, housing, leisure, and consumer goods. And what we found was that city-specific impact of the same lifestyle change option can differ by as much as a factor of 5, even within the same country. And we need both efficiency and sufficiency approaches to meet the 1.5-degree climate goal. So our study has mainly 3 steps. What we tried was to estimate city-level household carbon footprint with mixed unit approach, which means that incorporating physical unit of consumption because it can model changes in consumption patterns more realistically than monetary information. And it utilizes widely available statistics such as consumer expenditure survey and retail price data combined with an input-output approach. Then we model city-specific footprint reduction impact from lifestyle change options based on the concept of adoption rate. And finally, we modeled aggregated impact considering the overlaps between multiple lifestyle change options and explored how we could achieve the climate goal with scenario analysis approach. So this is a list of lifestyle change options analyzed in this study. We covered a variety of demand-side solutions, including adoption of end-use technology, shifting between consumption mode, and broader behavior changes. And it is one of the studies with the most extensive coverage of consumption-based solutions. And this is an example of the quantified carbon footprint reduction impact from a variety of lifestyle change options. And as you can see, the impact varies significantly between cities by as much as a factor 2 to 5. This implies that the priority solutions are different among cities, even in the same country. And our scenario analysis indicate how city-specific carbon footprint reduction pathways are different. And we found that either sufficiency approach, which is broader behavior change and shifting consumption patterns, and efficiency approach, adoption of end-use technology alone is not enough. We need both approaches to achieve the climate goal. So this provides insight on the prioritization of mitigation effort from consumption perspective and informs city government policies and stakeholder actions. So thank you very much for listening, and see you later in the Wonder Room session. So that's it from me.
All right, thank you so much for keeping the time. And so our next presenter, Yongju Jiang from Korea University. The floor is yours. So would you like to share your screen from your side? Okay, go ahead.
Hello everyone, I'm Yongchul Jiang, a PhD student at Graduate School of Energy and Environment at Korea University. Today, I'd like to present our study on establishing plastic physical accounts of Korea. As one of the top producers and consumers of plastics around the world, Korea has been experiencing problems such as collection interruption, illegal exports, and abandonment of plastic waste, particularly since 2018. In response, Korea has announced a series of policy interventions, including the first national plan on resource circulation. As a first step to understand Korea's contemporary management of plastics, our study conducts a material flow analysis between 2017 and 2019, when Korea experienced the most dynamic changes in the plastic value chain. The result of material flow analysis for 2017 showed that Korea's per capita plastic consumption and waste generation was 135 kilograms and 138 kilograms respectively. These were at higher levels than other major countries investigated. Compared to other countries, Korea showed relatively low landfilling rate and high recycling rate, which seems to be the result of the implementation of various policies such as extended producer responsibility. Plastic production and consumption in 2018 and 2019 did not change much compared to those of 2017, but the amount of plastic waste had kept increasing significantly along with the recycling rate. However, closing the loop for plastic flow require further improvements. Korea not only needs to reduce plastic consumption itself, though innovative business models and product design changes, but it also needs to strengthen and stabilize recycling markets by promoting high value-added recovery technology. Also, to better assess the potential contribution and feasibility of alternative options, more detailed and accurate data on the type of plastic polymers and the amount of recovery the resins, the virgin substitutes are required. Thank you for attention.
All right, great. Thank you for keeping the time. And our next presenter is Yiling Xiong from Beijing Normal University. And the floor is yours.
Hi. Can you hear my voice?
Yes.
Oh, okay. Hi, everyone. My name is Yiling Xiong. I'm from Beijing Normal University. Today, I'm very glad to give a brief introduction on my previous work. This work focused on China's water pollution issue and tried to identify and explore the dilemma between the regional water pollution and their economic growth. Actually, it is a vital important matter to every economy in the interregional trade. We all know that trade can lead to the pollutant linkage and the uneven distribution of economic benefits. So what influence did every region undertake in the interregional trade, and how was the status quo of the inequality among the regions is conducive for us to better understand the limitation of predominant producer-oriented environmental regulations. In our work, we calculated the regional environmental inequality index in terms of water pollution and value added. We can see that northeastern and part of central and northwestern regions suffer from the most serious environmental inequality, while the eastern and southern coastal provinces benefited the most from interregional trade in 2015. To further explore the regions of the inequality, we investigated the flow and important paths across provinces and sectors of water pollution and value added by combining multi-regional input-output analysis and structural path analysis. Such inequalities are driven by the inconsistent net flows of water pollutants and value added, which was further explained by the uneven spatial distribution of key sectors, that is agriculture, food and tobacco, construction and hotel and restaurant. These key sectors are generally in high water pollution or strongly demand for water polluted intensive products. We can see that the primary flowing path is high water polluting but low value added agricultural products produced by inland provinces are processed for food and ultimately consumed by developed southeastern region. The balancing and coordinated development of regions is a common sustainable target for a nation and our world. And one of the most important issues is the environmental inequality caused by the interregional trade, but prevailing production-based policy ignore the problem. So more kinds of policies should be enhanced and fully implemented in conjunction with existing total quantity control so as to bridge the environmental compensation between the provinces occupying the best environmental and economic advantages and the ones in the worst inequalities. That's a brief introduction to our work, and thank you for your listening.
All right, and thank you, Yilin Xiong. And our next presenter is Tomoya from Tohoku University. Please go ahead.
Can you see my screen?
Yes.
Oh, hi, my name is Tomoya Sugiyama, and I am a student in the Graduate School of Environmental Studies, Tohoku University. Our work is to develop an IO-based model for supply chain risk analysis focused on the risk that collapse of tailing dams at mining sites. There are very few tools for determining the impact of tailing dam failures on the industrial structure of each country through the supply chain. Likewise, there is no comprehensive model to measure the spillover effect of such a disaster. This makes it difficult to discuss ways to minimize the impact of supply chain risks at the country level. We analyze the relationship between tearing down failures at mining sites and demand equivalent to $100 billion from the Japanese automobile industry. We used the database for tearing down failures between 1928 and 2020 for this purpose, with a focus on 2014. There were 4 steps in our research method. First, we categorize the risk factor and the impact of dam failures on the country-by-country basis. The effect on industry in that country and abroad was also considered. Various media and reports were used for this. And second, this information was converted to MRIO table. Third, dividing Z by the output of each industry, the extent of risk can be measured per unit of output. Lastly, supply chain risk table was integrated into the MRIO model. In this way, it is possible to analyze the direct and indirect risks on the capacity to fulfill one unit of final demand. This analysis shows that the total of 4 people died due to tearing down failures related to the demand for resources from Japanese automobile industry. The result of our study show that in countries where there are many tearing downs, the economic contribution to GDP from mining is also high. It is especially important to take measures to prevent tearing downs. This method can be used as a tool to consider the share of responsibility for tearing down crops in terms of both supply and demand. So that's it. Thank you for listening.
All right, thank you so much for your presentation, and thank you for keep your presentation within 3 minutes. And our next presenter is Chen Liu from University of Southern Denmark. And please go ahead and share your screen.
Yes, and can everyone hear me?
Yes.
Yes, thank you, Zhi.
Maybe you could zoom in a little bit. Yeah.
Zoom in a little bit. Yes.
Yeah.
Let me see. What about now?
No, I think no, we cannot see your poster.
Here. What about now? I'm sorry.
Okay, I think it's fine. You can get started.
Yes. And yes, good morning, everyone. And my name is Chen Liu, and now I'm a PhD student in University of Southern Denmark. And my research interest is material flow analysis of metals. And today, this poster is presenting one of my work on building metabolism in China and its relevant to resource and environmental impact. And this work is supervised by Professor Gang Liu. And as we know that huge resources were consumed and a large quantity of greenhouse gas emission were produced in the whole life cycle of building, and especially in China, such large building constructing countries in the last few decades. And in this work, we have first counted building flows and stocks from 1950 to 2050 at the province level by dynamic material flow analysis method. And second, the construction materials consumption was calculated with the database of construction material intensities in Chinese single buildings. And lastly, there are around 8 billion tons of CO2 emission could be potentially reduced for the indirect carbon emission after detailed accounting by this work. And we think there are 3 highlights in this work. The first is that we have accounted the largest building construction country, China's building flows and stocks in a relative high resolution, which is at province level, and in a long time series, which lasts a century. And second, we have established a database of construction material intensities in Chinese single building. This database includes not only urban buildings, but also rural buildings. As far as we know, this is the first database comprising the first-hand data for the construction material intensities in rural China. And the third one is that we have calculated the indirect carbon emissions, which is less focused in previous researches. So please feel free to contact me if you have any questions, and I will be very glad if we could collaborate in buildings or other fields in MFA or in industrial ecology. And thank you, that's all by my side. Yes.
All right, impressive study. And our next presenter is Min-Hee Song from, again, from Korea University. And yeah, you could go ahead and share your slides or your poster from your side. Right.
Hello.
Hi. Yeah. Go ahead.
Yeah. First, I appreciate you giving me opportunity to share our ongoing research. In this story, we aim to provide the first estimate of carbon mitigation potential of modular and modular construction compared to reinforced concrete building in Korea. This is the Korean government set the goal to achieve carbon neutrality by 2050. However, it seems to be difficult to achieve this goal with zero energy building and remodeling building. As a circular economy standard, resource efficiency should be considered in the building life cycle. That's why we would like to focus on modular building that could improve productivity, recycling, and reduce waste. Our study compares the life cycle carbon emission between modular construction and traditional on-site construction. Our study analyzed a case of residential building that is proposed designed to compare the impact of modular construction and the traditional on-site construction. As for the traditional building method, the reinforced concrete construction, which is the most typical building in Korea, so we choose that. So here is the system boundary. We received the peer data from construction company. Our materials and processes that differ between two buildings are included in this study. We extracted data on the use of materials and the energy for various types of construction work. The environmental impact of each material was selected and matched by referring to previous studies among the eco-invent data. So workers' committee and the waste the emission per square meter were about 140 kilogram and 153 kilogram per modular and reinforced concrete respectively. That is the emission were lower per modular building. In previous study, modular construction produced lower emission compared to conventional building, but the difference is dependent on the building materials. In the material sector, the effect of ready-mixed concrete and then steel accounted for 81% in modular and 93% in reinforced concrete. More specifically, in the previous study, the proportion of the two materials was also high, but it was found that the proportion of ready-mixed concrete was particularly high in Korea building. We found that material selection is more important for reducing carbon emissions. We plan to include the data on the waste and the workers' committee to future interviews. I appreciate you listening to our study. If you have any questions, please let me know later. Thank you.
All right, great. And our next presenter is Xianghui Kong from Shandong University, China.
Hello, everyone. Can you hear me?
Yep.
Hello, everyone. Great pleasure to share my poster. The international shipping industry accounts for transporting 80% of the world trade. Shipping is the lifeblood of the global economy, and ships are the basic elements of maritime transportation. The booming international trade drives the expansion of the merchant fleets, which consume a tremendous amount of steel as the key material for shipbuilding. A detailed understanding of ships and associated steel stocks in use is essential. for anticipating future scrap available. Projection of recycled steel from the shipping industry may help sustainable manage the waste of end-of-life ships and reduce future material exploitation and associated environmental impacts. Here we quantify the steel stocks and flows of 5 types of ships global from 1980 to 2019, and project recycled steels from shipbreaking by 2050. We found that the steel stocks of ships increased by 2.9 times from 1920 and 2019, to which the top 2 contributors, Asia and Latin America and the Caribbean, was responsible for 32% and 28% of the global total increment. The fast-growing steel stocks used in ships in developing economics was the power source for the growth of global ship stocks, with 4.2 times increase in the study period. The rapid increase of stock is accompanied by a fast increase in steel scrap from the ships, reaching 9.9 million ton per year in 2018. Our projections from the future trades of steel used in ships from 2020 to 2050 shows that the steel from scrap ships worldwide will reach around 38 to 47 by 2050. This will impose a great challenge on coordination and actions to address such booming waste. More ships recycling facilities are needed, and we call for more sustainable and green method to recycle steel, which realize the steel development of circular economy by identifying the stocks and flows of steel used in ships. This study provides insights for the steel waste and the recycling management of end-of-life ships worldwide. Thank you, that's all.
All right, great. And everything's going great. And our next presenter is Resmond.
I'll be sharing my screen.
Yeah, go ahead.
Hello to everyone. I'm Resmond Reaño from the University of the Philippines, Los Baños. I'm here to present our study about the life cycle assessment of a university office building and the impact of steel recycling through sensitivity analysis. The construction industry is one of the most significant sectors in developing countries. However, the impact of the construction sector to the environment is overwhelming, accounting for the highest of global energy-related carbon dioxide emissions and the largest share of global final energy consumption in 2019. Out of the 38% of the global carbon dioxide emissions, the building's use or the operation phase accounts for the 28%, while building construction stage accounts for the 10% of emissions, mainly from material production. Life cycle assessment, or LCA, is a standardized tool that can be used to measure a building's embodied emissions and assess the success of mitigation methods employed. So LCA is defined in ISO 14040 as a technique for assessing the environmental aspects and potential impacts associated with a product or process. LCA accounts for the environmental impact from energy and material flows, such as emissions to air, land, and water, and resource and energy consumption. Moreover, only LCA provides a holistic picture of the environmental impacts of a product, not only the net carbon, but also the other emissions to supplement decision-making regarding trade-offs between product alternatives. LCA was performed based on a university building engineering drawing, accounting for the embodied emissions from the use of materials and during its construction stage, and the emissions during its operational stage and demolition. The operation stage has the highest greenhouse gas emissions and acidifying emissions, while the construction and material production stage have the highest impact on abiotic or metal depletion. On the major material use, steel manufacturing has the highest impact, followed by concrete, despite the latter composing about 90% of the built structure. Recycling steel by 50% could decrease the environmental impact associated with the building construction by a range of 10 to 20%. For future studies, the team will perform more sensitivity analysis on mitigation measures to further lower the impact of the built structure. So this will include use of eco-friendly materials for construction and use of renewable energies for the use phase. So that's all. Thank you, guys.
Okay, thank you, Resmond from University of the Philippines, Los Banos. And our next presenter is Xiaochun Hu from Capital University of Economics and Business. And the floor is yours. Hello? Is Xiaochun here? Okay, so let's move to our next presenter. Wait. Is Xiaochun Hu around? Okay, let's move to our next presenter. Our next presenter is Sun Ten Xu from Beijing Normal University. Please go ahead and share your screen.
Hello, everyone. Our work focus on changing patterns of China's regional transportation system. And we study this issue from a perspective of in-use steel stocks. As we all know, transportation plays an important role in boosting the economy. In recent years, the rapid development of China's transportation systems has driven a continuous accumulation of steel. Meanwhile, the scale and structure of transportation systems are different in different regions of China. In this study, we estimated the in-use steel stocks of 34 infrastructures and vehicles in railway, road, and subway systems in 31 provinces of China from 1990 to 2019, based on a bottom-up approach. The results show that China's steel stock in the transportation system has increased to 575 million tons in 2019. There are 197 million tons for infrastructure and 377 for vehicle. Spatially, there are 6 diversified changing patterns among 31 provinces. Steel stocks tend to decrease from the east to western inland areas. The Gini coefficient curve of the province's stock shows an inverted U shape over time, indicating a shrinking regional gap in recent years. This reflects a transition from efficiency to equity. We also measured the steel stock productivity, that is GDP per stock, in different regions, and observed its 4 diverse evolution types. The stock productivities in all regions climbed up initially, but show a decreasing trend in recent years. The most obvious decrease of stock productivity is observed in Western China. For Eastern regions, vehicles have been the main growth point in recent years, while Western regions are vigorously developing infrastructure. Our results help to illustrate the development status and spatial structural distribution of China's transportation system and could facilitate improved efficiency and the management of future challenges in China's transformation and development. Thank you for your attention.
Thank you, Shenten Xu. And our next presenter is Resmont, another life cycle assessment study.
Good day, everyone from the Philippines. Can you hear me clearly?
Yes, sorry.
Okay. I am Engineer Maricel Eneria, colleague of Dr. Resmond Riaño from the University of the Philippines, Los Baños. And let me present to you our poster entitled Assessment of the Embodied Environmental Impact of a Reinforced Concrete Building in the University. So this study was guided by ISO standards on life cycle assessment. And the main goal of the study was to evaluate the embodied environmental impacts of major construction materials such as concrete, steel, and wood. So roof trusses are made out of wood, and the building was built around 1960s. So this study focused from mining and manufacturing phase to construction phase. In short, buildings cradle to grave. Some data are not available, especially during the operational phase. So the construction materials mentioned were estimated using the engineering drawings provided by the planning office of the university. So the emissions were determined using the OpenLCA software with EcoInvent 3.6 database and CML 2001 methodology. So the impact categories considered were acidification potential, global warming potential, stratospheric ozone depletion, photochemical oxidation, eutrophication, terrestrial ecotoxicity, abiotic depletion, fossil fuel depletion, human toxicity, and ecotoxicity in marine, aquatic, and freshwater. Sensitivity analyses were also performed by increasing and decreasing door and window openings, replacing roof covering with clay tiles, and replacing wooden truss with steel. So based on results as shown in figure 2 and figure 3, let me zoom in. So it was found that the manufacturing stage had the highest contribution for 10 out of 11 categories, so except for the eutrophication, followed by construction stage and transportation stage. The impact of mining and manufacturing can be attributed to the high utilization of fossil fuel and other resources and treatment of waste during materials production. Despite only comprising about 6% of the total building weight, the reinforcing steel had the highest contribution in all the impact categories, except for the abiotic depletion, so which was dominated by galvanized iron sheets, the roof covering. So consequently, steel followed by concrete and then wood was found to have the highest contribution to the mining and manufacturing stage. So the high contribution of steel can be attributed to the massive fossil fuel consumption for its production processes occurring at a very high temperature. Also, based on sensitivity analysis, as shown in figure 3, varying the opening of windows and doors is deemed insignificant in reducing the environmental impacts of the building. So for future refurbishments of the building and future green building design, using Roman clay tile roofing is recommended over the GI sheets because of its reduced impacts. Also, utilizing wood for trusses and purlins instead of steel was found to have significant environmental savings. Therefore, wood is also recommended. Thank you for listening.
Okay, great study, Maricel, and from University of the Philippines. And our next presenter is Kai-Xing Huang from Northeastern University, United States. And the floor is yours. Hello?
Hi, I don't think I can share the screen from my side.
Maybe Maricel, could you stop sharing your screen and then Kai-Xing could share her screen? Because let me see if I can stop sharing. Okay, I think
here we go.
I think you're okay to go. Yeah. Are you able to share your screen right now?
Yeah, I think so. Can you see
Okay,
it?
great. Go ahead.
Yeah, hello. Can I start?
Yeah, sure.
Okay, hello everyone, I'm Kai Cheng. I'm from Northeastern University based in Boston. Today I want to share my research, which is appending material flow to the National Energy Modeling System for projecting the physical economy of the US. So basically, if the world wants to achieve more sustainable development, the ultimate goal is that we want to decouple the resource, environmental impacts, and health impacts from the economic and population growth. So in other words, we still want the economic growth fast, but at the same time, we hope we can use less resource energy, emit less air pollution. So that means the future projection under the different scenarios are really informative for us to prepare or switch our plan to adapt to the future. So taking the advantage of the technology-rich energy model, such as detailed sectorial information and easy to do the scenarios analysis, we have developed this method to append the material flow to the NAMES model. So bit background of the NAMES model, it is an official model used by USEIA to provide the energy projection data for the annual energy outlook. We have extracted the economic activities from the names. At the same time, we have used the trade information from a database called UN Comtrade. So it is a database built by the UN to document all the trade information among countries. So basically mapping the industrial in the names with the commodities in the UN Comtrade database, and then calculated the imputed prices for the names industry and finally convert them to a physical resource flow. So here are some examples of the physical resource flow we got, including the non-manufacturing and manufacturing industries under different AEO scenarios. Most of the industries are following the trend of the mineral extraction results, which is largely affected by the economic growth. We have also calculated the material intensities in the future. As we can see here, that extraction intensity per GDP will decrease in the future, while the intensity per capita is still increasing. The decreasing trend of the intensity per GDP indicates that the physical resource decoupling in the US economy, and it is also following the goal of the International Resource Panel, which aim to reduce the material intensity in the future. The increasing trend of the intensity per capita is mainly driven by the mineral extraction increasing, which need to meet the demands of the construction, and at the same time, the projected population growth is way slower than the construction output growth, so that make the increasing trend of the intensity per capita. So a couple of key takeaways here. So the analysis demonstrates the feasibilities of the harnessing names to create scenarios of the US physical resource flow. Names and other energy system modeling therefore provide a convenient scaffold from which to estimate the future physical resource flows. So this analysis presented here estimates the material flow outputs from the oil extraction and manufacturing sectors, thus representing the entire physical economy of the United States. So happy to discuss in the breakout room. Thanks.
All right, Kai-Xing Huang, and great presentation. So today we had a lot of great posters, and we can continue the discussion in the Wonder platform. And I have already shared the link to Wonder, and there you will find the poster presenters in different lounges. And thank you for participating in the Asian Pacific poster session, and thank you for the support. And that I will see you in the Wonder platform.